Why? You just feel like
Or just very nice.
that's good. That's very helpful. Oh, okay. Okay, let's get started again, please. Okay. So, yeah. So there are a couple more things that I wanna hit on. The maybe the first one is evaluation of integrals. Evaluation of integrals using series. Okay, so evaluation of definite integrals using series. Okay, I'm just going to do one example, which is the integral from 0 to 1 of e to the negative x squared dx. Okay. So, right. So the problem with this integral, as we said before, is that there's no antiderivative, right? There's no simple way of writing an antiderivative. Actually, we know a way now, right? We can use power series, right? So what we're going to do is we say, okay, e to the negative x squared is summation negative x squared to the n over n factorial from n equals 0 to infinity dx. Right? That's to say negative 1 to the n x to the 2n over n factorial summed between 0 and infinity and integrated between 0 and 1. Right? So we just replace this thing with its power series, and we're integrating a power series. Right? So remember, for within the domain of convergence, it's okay to switch the order. It's okay to switch the order. So we switch the order because the domain of convergence is the whole line. Right? So we switch the order and we get the integral. We get the sum of the integrals from 0 to 1 of negative 1 to the n x to the 2n over n factorial dx. Right? And so what's that? That's negative 1 to the n x to the 2n plus 1 over n factorial times 2n plus 1, evaluated between 0 and 1, and summed between 0 and from 0 to infinity. Okay, but what's that? Right? When you evaluate each of these guys, you get the sum, the difference between this at 1 minus this at 0. This at 1 is just going to be negative 1 to the n over n factorial 2n plus 1. Right? This at 0 is just 0, so we don't get anything from the 0 term. Okay, so that allows you to evaluate the definite integral. That's the value of the definite integral. What you see here is that we have an alternating series that gives us the value of this integral. Okay, and right, if you want if you want to get some approximation, you can use the alternating series to approximate. You can get the alternating series to approximate the integral, right? So if you work out the values, it turns out to be like 310 minus 14, 216. 3, 42, 216. So you get this alternating series, and you can sum it up. You can take the partial sum, and that will give you some approximation. So that's just one thing that I didn't mention earlier, but I think it's kind of cool, right? You have this integral, you don't know how to evaluate it, but with infinite series, you can get the exact answer. You can get an expression for the exact answer, and luckily for us, it's an alternating series. We can get approximations, and we know the errors, right? Remember, if we sum up to here, the error is this, right? If we sum up to here, the error is at most 1/42. If we sum up to here, the error is at most 1/216, right? So the alternating series are very, very convenient. Do you have a question? No? Okay, so that's just one thing that I wanted to mention, and then the last thing I want to mention is the binomial series. Okay, so let's call it the binomial series. Okay. So that is your function is 1 plus x to the k. Your function is 1 plus x to the k, and you'd want to get a power series for it. So you want power series expansion. Around 0. So you know what to do, right? You take your derivatives, right? The first derivative is going to be k 1 plus x to the k minus 1, right? Second derivative is going to be k minus 1 plus x to the k minus 2, etc., etc. Right? Oh, and I should say that k is a real number. Okay, so it's not k is 2, or it's not an integer, but k is some, k could be 1/2, k could be pi, right? It could be anything like that. Okay? Okay, and then you evaluate, right? F at 0 is 1 to the k is 1. F prime at 0 is k. F double prime at 0 is k times k minus 1. Right? Dot, 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 right? Fn at 0 is k times k minus 1 times k minus 2 times k minus n plus 1. Okay, and then you set up your power series, right? So the power series is going to be summation k minus 1 dot 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 k minus n plus 1 better. Over n factorial x to the n from n equals 0 to infinity. So 1 plus x to the k. What's this? Okay. And this thing here, this term, this coefficient here is denoted k choose n. K choose n. That's how you read this. K choose n. So just a remark, if k and n are natural numbers, then k choose n is the number of ways to choose k objects from a set of n. That's why it's called choose, k choose n. It's the number of ways to choose k objects out of n objects. Wait, I got it backwards. Sorry. Choose n objects from a set of k. Sorry. Okay. In any case, you have this thing, the binomial series, 1 plus x to the k equals summation, right? K choose n over k choose n times x to the n. So you have an expression for this sort of thing. Okay, and it turns out that this is valid. This is valid in, so the radius of convergence is 1 for this. So only for x between -1 and 1. Why does 2 something get -1? Okay. Okay. So let's finish up with one final example. Okay. So here it is. F of x is 1 over the square root of 4 minus x. Okay. And we'd like to express this thing as a power series. So express as a power series. And what we're going to do is we're going to be clever and use the binomial series for this. Okay. Right. So here's what we're going to do. We're going to rewrite this as the square root of 4 times 1 minus x over 4. That's to say 1/2 of 1 over the square root of 1 minus x over 4. Okay. But now you see, right, here is a binomial, here is the binomial thing here, right? Right, you have this, right? This is 1/2 x minus, 1 minus x to the 4 to the negative 1/2. Right? And we have an expansion for that, right? That is 1/2 summation, right? Negative 1/2 choose n from n equals 0 to infinity, right? Times x over 4 to the n. And this is valid for x over 4 smaller than 1. In other words, between has to be between negative 4 and positive 1. Okay. Right. So you get right, 1/2 summation negative 1/2 choose n. X to the n over 4 to the n from n equals 0 to infinity. Right? And so that's your power series expansion. Yes? Oh, it should be negative. I'm sorry. Yeah, that should be negative. So you get negative 1 to the n. Anyway, this you know. I think of the things that I've shown you, you know, of the things that I've shown you today, I think the most important are, one, this way of solving differential equations by using power series, and two, maybe the evaluation of integrals using the power series. That's also pretty cool. And then this is sort of a, you know, like, it's interesting, but you don't see it very often. The really powerful thing is that application to differential equations. And if you take a course in differential equations, you'll probably see something like this. You'll see this and something a little bit more strong than this along the same lines. Okay, so that is the end of all the material. You made it. You made it to the end. Okay, good job. Good job. Okay, so yeah, I hope it was interesting for you, and that you have some sense of you know, what you can do with you know, not just, you know, differentiation and integration, but really with power series. I feel like power series is sort of the big goal, the main thing that you want to get out of this course. Okay, so that's it.